They won't be able to hear the audio is through his computer.
Okay. Say it louder. Are you ready?
Yes, I'm ready. Yeah.
So welcome back, everyone. Our first speaker today is not Hogancamp, and I forgot to check that.
Yeah. No, that's right. Yeah.
And he's going to tell us about the Kirby color for Khovanov homology. Thank you.
Awesome. Well, thank you very much for the invitation to be here. I just want to say, last time I was in Athens, actually the only other time I was ever in Athens was for the big 2-week-long Georgia Topology Conference in 2009. So that was my very first conference going experience, and it was pretty awesome. Anyway, so very happy to be back, and thanks everyone for being here in one way or the other. So what I'll talk about today is joint work, where, you know, it's hard to predict the things, but very much hoping this will be on the archive soon. But it's not yet. So it's a joint work with Dave Rose and Paul Wedrich. And also it's very much, what we were thinking about initially in this kind of project was we wanted to understand, or basically better understand a construction of Manolescu-Neithalath. So a lot of what I'll be talking about today is a sort of maybe a reinterpretation or a refinement of something they, so basically a description they gave of this 4-manifold invariance called the skein lasagna module. Anyway, so they basically, so Manolescu-Neithalath have this understanding of what the attachment of a 2-handle does to this skein lasagna module. And Dave, Paul, and I wanted a like sort of an abstract way of understanding this in terms of satellite operations. Anyway, so for the talk today, I'll take as my main motivation the satellite operations in Khovanov homology. So so satellite or cabling operations in Khovanov homology are governed by what we call the annular Bar-Natan category, which we saw a little bit of in Gage's talk yesterday, and we're likely to see more of later this week or later in our lives. Anyway, so with this category, I'll describe it in detail later. But yeah, it describes the sort of natural relationships between the Khovanov homology of, so you fix your favorite framed knot, and you look at the Khovanov homologies of cables of that knot. The annular Bar-Natan category, in essence, describes the natural relationships between those Khovanov homologies. So, okay. One way of saying that is if you have a framed, well, more generally a framed link, the functoriality of Khovanov homology with respect to cobordisms actually gives you a functor from many copies of this annular Bar-Natan category into the world of bigraded vector spaces. So objects of here represent the kinds of ways we may cable our link, and morphisms in here describe relationships between those cables. Okay, and then notation wise, I'll temporarily denote this cabling operation by the Khovanov homology of a link relative, you know, colored by these various labels. And just this is I really should write this in extremely large, bold font. This is extremely naive. This is way, way, way too naive, because what have we done? We've taken homology. We've taken homology, Khovanov homology, which we sort of have taken homology too early. So one of the things that I do want to point out, even though it's not going to be a super big deal for this talk, the annular Bar-Natan category is just an additive category. There's no like complexes or anything here. And then objects over here are also just bigraded vector spaces. They're not chain complexes either. We've taken homology already in order so we can discuss functoriality of the Khovanov invariant. But if we had something which was like a chain complex in the annular Bar-Natan category, for example, we might take the object representing, so objects of the annular Bar-Natan category, I said, will represent ways that we may cable our knot. So here's a sort of a, you know, an object of the annular Bar-Natan category, but we may, instead of considering sort of these trivial ways of cabling or not, we may consider slightly more interesting ways of cabling or not. For example, instead of doing a trivial cable, we might do a trivial cable with like with a twist. And then the only way we can understand this in the annular Bar-Natan category is we understand this as a chain complex of objects in the annular Bar-Natan category. And so when we map it over using the functoriality of Khovanov homology, we get a complex of bigraded vector spaces. But that complex is not the same thing as just taking Khovanov homology of the actual cable. We've taken homology sort of too early. So in general, a more sophisticated notion of cabling would involve complexes at every stage. And we're not going to do that today. We are going to be extremely naive today. And we'll be happier for it. Okay. Okay. So, so the goal today is to, I'll remind everyone or define, maybe you'll see this for the first time, the annular Bar-Natan category. And I want to, so the main motivating thing is I want to have an element in this annular Bar-Natan category, which is invariant under handle slides. This is very much reminiscent of, you know, how one defines their Reichenstein Thrive invariance or whatever, is you start with the link invariant and you define whatever, an element in the skein module of the annulus, satisfying, which is under handle slides. So today I will define an element which is invariant under handle slides. It may not be the only sort of thing you can do, but it will be invariant under handle slides, which we think is very cool. But it's not actually going to live in the annular Bar-Natan category. It's going to live in some co-completion. So the thing that I define will be a co-limit of sort of finite things. So it's not going to be an object. It'll be an end object, if you know what those things mean. And then the relationship to this skein lasagna business is still a conjecture, but I think it's probably true, that basically just by comparing what we define with the Manolescu-Neithalath formula, the conjecture is that if you color every component of a framed link by this Kirby color we define, what you get is a description of this skein lasagna module of the 4 manifold obtained by attaching 2 handles to each of those components. All right, and the outline for the rest of the talk. So as promised, I'll tell you about the annular Bar-Natan category. There's a description of the annular Bar-Natan category, which is extremely convenient, called the dotted Temper-Lelieb category. This will enable us to draw simple pictures to represent complicated cobordisms. And in that category, I'll define the Kirby color. I'll describe the handle slide move. And then I had originally planned on talking more about the lasagna skein module, but I suspect we won't actually get there. Okay. So first things first. So I want to remind everyone what is the Bar-Natan category. So the input for a Bar-Natan category is an oriented surface, possibly with boundary, and a finite collection of points on the boundary. The Bar-Natan category itself is, and for this talk, I don't want to worry about denominators or anything. Anyway, so I'm going to be working over a field of characteristic 0, so I could divide by stuff. And the objects of this category are just embedded 1 manifolds with this prescribed boundary. Morphisms are basically cobordisms between those tangles, but because our tangles have boundary, our cobordisms will have corners. We allow formal linear combinations of cobordisms and impose the following relations. So the sphere, if you ever see a component in your cobordism, which is just a 2-sphere, then that whole entire cobordism is set equal to 0. If you see a closed component which is a torus, you can delete that component at the expense of multiplying by 2. And if you see any other closed oriented surface, your cobordism is 0. So closed surfaces evaluate in this following way. The only interesting one is the torus, and the others are 0. And we have this net cutting relation. So the identity cobordism of a circle decomposes as a sum of these two pictures. And we use a dot to be shorthand for 1/2 times a handle. Those of you who like this kind of thing, keep in mind that, so we'll be talking about idempotent decompositions in like categories. You know, we know what a direct sum decomposition of vector spaces is. But here we're talking about categories which are some like abstract categories defined by generators and relations. So like the objects are not vector spaces, or they're not like sets or things like this. So what does it mean to discuss direct sum decompositions? Well, in this abstract world, a direct sum decomposition is just a decomposition of the identity morphism of an object into or a sum of orthogonal idempotents. And the little nugget of information that I see a lot of grad students here. So I want to like aim my talk maybe somewhat at you guys. So this is for the grad students or the newcomers to the subject. So here we see the identity endomorphism of a circle equals the sum of two things. And I'm claiming that these two things are in fact idempotent, meaning if you square them, you get themselves. So if I stack 2 copies of this dude on himself, I see 1/2 times a torus. See, remember the dot represents a handle. So a sphere with a dot represents 1/2 times a torus. And my rule for evaluating surfaces tells me I can just delete that thing at the expense of multiplying by 1. And we've just seen that this little sum and on the right hand side is in fact an idempotent operator. And this other dude is also an idempotent. These are 2 complementary idempotents. And so this net cutting relation is basically just telling us that the circle itself in this weird category splits up as something like a direct sum of 2 copies of the empty diagram. So this is a categorical version of the statement that the circle should evaluate to 2. Okay. Yeah.
If the morphisms are rational linear combinations,
Yeah.
not the object, but the object, they're not human combinations.
Exactly.
So in other words, if I take a linear combination of coordinates, they all have to have the same.
They all have to,
ends.
yes, they have to have the same source and target. Exactly. And you mod out also, I didn't say this, but you mod out the cobordisms. Cobordisms, you should also impose the isotopy rail boundary relation. So 2 cobordisms are regarded as equal if they're isotopic rail boundary. Okay. Yeah, they're orthogonal. So like complementary means you sum to the identity and you pairwise multiply to 0. So these are orthogonal because like if I put this one on top of that one, I get a sphere, which is 0. And if I put them in the other way, I get a genus 2 surface, which is 0. Yeah, 2 dots, each dot is a handle. Well, it's a half handle. So I get 1/4 times the genus 2 surface. 1/4 times 0. Yeah. This is good stuff. I mean, you are absolutely right. Yeah. Thank you. Okay. That was fun.
Matt, can I ask something?
Yes. Hi.
Hey, Matt. When you're doing this in a surface, I've of course seen this in the setting when the surface is a disk. But here, your sigma could be any surface with boundary or not with boundary.
Yeah, in principle. And then our cobordisms will live in surface cross I.
And do you have to worry about, for instance, for the torus relation, like whether that torus is trivial in the homology of the of the surface, or is it only for like?
I suppose these should all be relations inside a ball. So these are all bound handle bodies. Yeah.
Got it.
And then the net cutting relation should also be like a null,
Null disk, yeah.
Yeah. Okay. Good
Cool.
question. By the way, sorry, I didn't repeat the question. Was it audible to people? So, okay. Okay, great. Awesome. Yeah. So, okay. And then a standard thing to do that I won't maybe write, but is also lurking behind the scenes, is we'll take this category. So this category, what kind of category is it? So the morphism spaces are Z graded. So we'll declare that the degree of a, like a cup or a cap is -1, the degree of a saddle is +1. And because a dot represents a little handle, that's 2 saddles. So the degree of the dot will be 2. So this category, the technical way of saying it is that this category is enriched in graded vector spaces. So it's a linear category, and then the OBs are Z graded. What we'll do to this category, just for simplicity later, is we'll formally adjoin all direct sums, finite direct sums, and all grading shifts. So we can speak of objects which are not just tangles, but rather formal direct sums of tangles. Morphisms in this additive closure will be matrices of morphisms in the. I'm happy to say more about this, but maybe that's a little too much for a talk right now. So I won't distinguish my notation between the original Bar-Natan category, whose objects are just tangles, and then the Bar-Natan category, whose objects are like formal sums of shifts of tangles. Definition: the annular Bar-Natan category is just the Bar-Natan category associated to the annulus with empty boundary. And we visualize morphisms in this category via their cross sections. So, for example, a typical morphism in the annular Bar-Natan category, I'll draw the sort of puncture, the whole of the annulus cross I. I'll visualize that as just sort of like a little axis, central axis in all of my diagrams. And this little cake, upside down cake pan kind of thing, we'll visualize just by its cross section. So this is a great simplification. This above picture is very hard to draw, but is much easier to draw just a single cup. Identity cobordisms will be visualized by just their cross. So the cross section of this cobordism is just 2 vertical lines. If a sheet happens to have a dot living on it, then I'll just place the dot on my diagram in the obvious way. So this identity cobordism with a dot on the outer sheet, the corresponding cross section gets visualized in this way. Maybe I didn't say this clearly enough, but 2 dots on any sheet is 0. Because 2 handles on any sheet, well, you should think of this maybe as, this might be a relation that I have to impose kind of, no, actually it's 0 by the net cutting relation. Yeah, so a punctured genus 2 surface, exercise for the grad students or whatever. Dang it. Genus 2 surface kind of coming off of a sheet like this is automatically 0. Therefore, 2 dots on a sheet is 0. Okay. So anyway, so we're describing the annular Bar-Natan category by cross sections. What we get is this category called dotted temporally Lieb. And it's, strictly speaking, it's not dotted temporally Lieb. It's dotted temporally Lieb at the parameter equals 1. Anyway, so I'll define this category. So the objects of this category are parameterized by non-negative integers. Think of these objects as being just a sequence of dots on a line, or maybe algebraically, it'll be useful to denote them by just sort of this symbol. So v to the power n is just some symbol that denotes this object, my category. Morphisms in this category are generated by the cup, the cap, and the dotted identity, generated in the sense of, so the dotted temporally Lieb category is going to be a monoidal category. So I can stack diagrams side by side, or I can place them on top of each other. So these morphisms generate with respect to both planar ways of composing things. And we impose the following relations. So the unknot is worth 2, the dotted unknot is worth 0, and then this funny relation here So these relations exactly mirror, or they're sort of cross-sectional versions of relations that we already have in the annular Bar-Natan category. So that's encoded here. So this dotted temporal lead category is in fact equivalent to the annular Bar-Natan category. So for example, the relation that tells you that an unknot is worth 0, well, that's just this relation in the annular Bar-Natan category. So unknot, a circle here should be thought of as the cross-section of a naked, an undotted torus. And then how do we evaluate a torus in the annulus? Well, we net cut somewhere. So we net cut, for example, along this green curve, and we get a sum of two terms, this one and that one. The dot is either here or there, but either way, this is a dotted sphere plus a dotted sphere. Each one of those dotted spheres is 1, so we get this relation. Okay, so the unknot relation is is a cross section of this relation. The dotted unknot relation, if you had a dot somewhere, on this torus, then you would have 2 dots on this picture and 2 dots on this picture. Both of them would be 0, and that gives you this dotted temporal lead relation. This relation is the most interesting one, and that follows from being able to, so that follows from this picture. So here we have, so here's a picture of a morphism in the annular Bar-Natan category. And up to isotopy, this cobordism, this morphism is equal to that morphism. And I can net cut in 2 ways. I can net cut along sort of curve like that curve, or I can, on the other side, I can net cut along this little curve. Net cutting along the blue curve gives me the left-hand side of this equation. Net cutting along the green curve gives me the right-hand side of this equation. And so that's a little just explanation of this relation. So this is the annular Bar-Natan category, described 1 dimension down, described by this temporal lead category. Okay. So the goal is to describe an interesting bunch of objects in the annular Bar-Natan category, or we'll have to complete the annular. We've already completed the annular Bar-Natan category with respect to the operation of taking direct sums and grading shifts. We'll have to complete it with respect to other operations. We'll need to throw in direct summands of objects, and we'll need to throw in certain kinds of colimits. Anyway, but after we throw in, whatever additional objects we need, the next goal is to construct an interesting object in there, satisfying handle lines. Okay. Are there any questions? Yeah.
So this relation comes from sphere, right?
This relation? Wait.
No, like this surface we draw.
What is, you mean, so topologically, what is this? This is it's 2 annuli with a tube between them. It's a, yeah, so you have like, you have a cake pan. Sorry, this is an awful picture. And then you have an upside down cake pan, or sorry, yes.
So that first thing was a cake pan with a table.
Yeah, I'm sorry. So what are these pictures? So what you're supposed to think of is you're supposed to take the identity cobordism. So just a cylinder on 2 circles, and fuse the 2 sheets together you do surgery. you fuse the 2 sheets together with a little hand.
So you just connect 2 of them, right?
Yeah.
So yeah.
Yeah.
It's like language the third way.
Oh, I'm sorry, guys. I have to take this. It's probably about my cat. He's getting surgery right now. Hello?
So that, see, I thought we were just supposed to take two vertical strands, and just basically like surface of revolution, spin around, and dot.
Okay. Okay.
Let's see, like, yeah.
Okay. Can I call you back? I'm sorry. I'm in the middle of something right now. Are you looking to send it off? Yeah, I'm sorry. I need to call you back in about 40 minutes. Or you need me to decide now. It's going to be how much? Okay, yeah, just do it. Okay, bye. Yeah, sorry guys. That was a bad timing. Yeah. Yeah, he's got he had a growth on his face. Anyway, got it removed. Okay, thanks for hanging in there, guys. That was unfortunate timing. Are we good? Okay, so for the Kirby color, I need some more ingredients, some more background. So grad students are gonna learn some more interesting stuff before we're done. So we need some more ingredients. I need to describe. So I didn't say this well enough. I'm sorry. The annular Bar-Natan category has a monoidal structure because I can kind of place like I can place so that in the annular Bar-Natan category, I have an object like an essential circle or maybe two essential circles. The monoidal structure is given by placing a diagram in a neighborhood of the functor of the other diagram. And the dotted temporal leaf category also has a monoidal structure given by placing diagrams side by side. Obviously, these are compatible. So the annular Bar-Natan category and the dotted temporal leaf category are equivalent, not just as categories, but as monoidal categories. And what I need to introduce next is like symmetric powers in this category. So given the essential circle, I want to be able to talk about not just the nth tensor power of that circle, but rather the nth symmetric power of that circle. So for this, we need to define symmetrizers, and we need to pass to the Curvy envelope. The Curvy envelope is the sort of category you would get by adjoining images of idempotents. Anyway, so the symmetrizing idempotent is just the usual thing. I have to tell you what does a permutation look like. So the generating permutation should be thought of as a morphism in a dotted temporal leaf category by this little assignment. You can set, this is the sort of classic story that this assignment does satisfy the relations in the symmetric group. We get the symmetric group and not the braid group here because we're working really at Q equals 1. The symmetrizing idempotence is just the usual symmetrizer. You take the sum of all permutations. You regard a permutation as being a diagram by taking a string diagram. You normalize by dividing by the number of permutations. Okay, so that's the usual symmetrizer. This is the Q equals 1 version of what's called the Jones-Wenzel idempotent. Here's our first example. So the second Jones-Wenzel idempotent. So we have the identity, we have the interesting transposition. Their sum over 2 is this guy. So that's a recognizable formula for the second Jones-Wenzel idempotent at Q equals 1. Some relations that we have are these guys. Symmetrizers sort of, so you can define them as we define them, or you can also define them by this recursion, which is sometimes useful. Sometimes I call this projector absorbing. So a big symmetrizer absorbs a small symmetrizer. Symmetrizers kill turnbacks. This is related to the statement that a symmetrizer symmetrizes. So a symmetrizer absorbs crossings from above or from below. And that's very closely related to the fact that symmetrizers kill turnbacks. We have an interesting morphism, though. So the symmetrizer kills turnbacks, but it does not kill dotted turnbacks. So we have an interesting morphism involving dotted turnbacks now, because we have in the dotted temporal leap category. You know, at Brewery, you might think you have lots of interesting morphisms. You could do a dot here, like you could do a dotted cap any place on the bottom, but in fact, they're all equal. Okay, so these are symmetrizers. We now pass to the category that has images of these symmetrizers. So these symmetrizers are idempotent operators. If you symmetrize and then symmetrize again, it's the same thing as just symmetrizing once. So you should think of the symmetrizer as being like a projection operator, but it's acting on an object in some weird abstract category. So you have to sort of throw in as new objects images of all these projection operators. So that process is called taking the Kirby envelope. So the Kirby envelope of our dotted temporal leap category is the category we get by adjoining all direct sum ends of all objects. And again, there's a precise definition that's not so hard to state, but maybe not quite appropriate for a talk. So if you want, we can talk about this later or in the question session afterwards. For example, this relation of morphisms in the dotted temporal leap category corresponds to, in the Kirby envelope, an actual direct sum decomposition. You take the object represented, you know, this is the identity endomorphism of some object. And that identity endomorphism splits as the image of this idempotent and the image of its complement, direct sum together. So how are these? This is a formal object. This is an object of the Kirby envelope. The image of the symmetrizer is an object of the Kirby envelope, but it's not an object of the original category. The original category, we defined it by generators. I told you what all of the objects were. All the objects are just like, you know, integers, like dotted sequences of dots on a line. There's no object that corresponds to the image of. It's not as mysterious as I'm making it sound. I can easily say more, but I wanna. So let me say the following. So if you have if you have a linear category is just, you know, category whose Elm spaces are like vector spaces or K modules for some K. So if you have an endomorphism of an object which is idempotent, you know, satisfies E squared equals E, we say that this idempotent splits if you can factor it as, so if you can find another object in your category Y and a pair of morphisms with the relation that E is the composition of these two, and satisfying this. So your idempotent splits if you can factor it as the composition of two things which compose in the other way to give you the identity. And in that case, you would call Y the image of your idempotent E, or it's isomorphic to the image of your idempotent. But not every idempotent splits. You can't always find an object through which your idempotent factors in this way. And so the Kirby envelope is just a category you get by formally adjoining such objects. Anyway, and the point is, they're not objects, the original category, but you know everything about HOMs into and out of them. Okay. So, okay, now we're ready to kind of define the Kirby color. So we have images. So you should think of the Kirby color as being something like an infinite symmetrizer. Okay. So I want to take an infinite symmetric power of my V. So I would need like an infinite symmetrizer. But how do we deal with infinite things in analysis or algebra? Well, we define infinite things as limits or colimits or whatever. So like, for example, if you wanted to define an infinite, like GL infinity, you would look at the sequence of GLNs. You would say GLN includes in GLN plus 1, includes in GLN plus 2, and you can take the union. Okay, so when we talk about infinite things, we always need a direct system of like things, including in things, including in things, including in things, and then we can take the limit of that. So I want to do a very similar procedure for this Kirby color. So we have the 0 symmetric power, doesn't quite include, but it certainly maps to the second symmetric power via this dotted cup, and that maps to the dotted or the fourth symmetrizer, the fourth symmetric power via this other dotted cup, and so on. There's a parity thing. So like the dotted cup, you know, moves you from the image of pk to the image of pk plus 2. So in fact, there's two different directed systems we can define, starting at 0 or starting at 1. And in fact, this is a slight lie. The dot has degree 2, remember? So if I want my maps to be in the end homogeneous of degree 0, I better insert some grading shifts. So I'll insert grading shifts in this way. And I can define the two different Kirby colors, the even Kirby color and the odd Kirby color, to be the colimit of these directed systems. So that lives in yet a larger category where you called the end completion, which I will not describe in detail. Okay, now to give you guys some intuition about what's going on here, I think it's very useful to understand everything here in terms of a functor. So this dotted TL category is extremely abstract and kind of hard to fit in our heads. So there's actually a functor from the dotted TL to just graded vector spaces. You should think of this functor as being like, remember the dotted TL is supposed to be equivalent to the annular Bar-Natan category. And we have a functor that just sort of takes a circle and evaluates it in the plane, takes a Khovanov homology of the thing. So the generating object V, in the annular Bar-Natan category, this is just an essential circle. I can forget about the annulus and just take Khovanov homology, and I get the graded vector space, 2 copies of the rational numbers with shifts. And then the dot, that's an endomorphism of V, is just the matrix so it's an operator that sends this guy to that guy. This is like Khovanov homology of the unknot with its operator X. The symmetric powers, so the images of these symmetrizing idempotents, they go to the symmetric power of that guy, which, if you work it out, it's like a quantum integers worth of one dimension of like Q. So So you take n copies of, so you take n plus 1 copies, sorry. Yes. You take n plus 1 copies of Q, shift it in this way. Ah, dang it. Sorry, this is too sloppy. And the dotted cup morphisms. So this directed system should be thought of as being like, after you pass to the image of this functor, so you start with the 0th symmetric power, the 2nd symmetric power shifted down by an appropriate amount, the 4th symmetric power, and the maps in this directed system, the maps induced by these dotted cups, you have to define the functor in more detail than I've done in order to see this. But what happens is your directed system is just, so this guy really includes in the next one over, and that includes in the next one over. And the colimit is really like this union. And so you should think of the Kirby color under this functor as mapping to this infinite vector space, graded vector space, which is just the direct sum of Q's with shifts. Actually, under this functor, the even guy and the odd guy both have the same image. Okay, so that's how you should think of their Kirby color. And the theorem, well, there's a few things that I want to state. So theorem. So this dotted TL category with Kirby colors adjoined is a well-defined monodal category. So you can still define, we can still talk about, like, even though these things are, colimits, you can still make sense of what it means to kind of tensor them together. So you, that's still a monodal category. This is actually not saying very much. You have to kind of adjoin countable direct sums. So it's a little bit weird. I don't know, maybe I'll say almost. And we have some understanding of, like, the Kirby color tensor the Kirby color in this category. Some understanding of what it means to take, like, a Kirby color tensored finite object in this category. And the second theorem is that this guy satisfies the handle slide move. So inside, so to state the handle slide relation, we need to work in a different Bar-Natan category. So if we take the Bar-Natan category now of the annulus with 2 punctures, sorry, not with, sorry, the annulus with one puncture, but 2 boundary points. And we take this category and we have to complete it in the same way that we completed everything else. So we have to adjoin colimits, Kirby envelopes, and stuff like this. So inside this category, we have an isomorphism. And I'll say maybe a couple words about how one sees this isomorphism. So if you take a Kirby color kind of, so this is a well-defined object of this Bar-Natan category. Because remember, the Kirby color was defined as an object of dotted tempered Lediep. because dotted temporal leaf is equivalent to annular Bar-Natan, you can also regard the Kirby color as living in the annular Bar-Natan category. So this is a well-defined object of this completed Bar-Natan category. And then the Kirby color, the handle slide relation is it's this, but with a parity change. So the odd, when you slide a strand past an even Kirby color, you get the odd Kirby color, and vice versa. I want to say a word about where the maps here actually come from. And so this will be sort of probably the last thing that I do here. So to give some idea of why this is true or how this is proven, I want to first make the observation that inside this Bar-Natan category with two boundary points, we have a morphism so sorry, I need some. So this is going to be a little bit difficult because I have been drawing all my pictures in the dotted temporal leaf setting. Now I need to draw them in this annular world. So I want to introduce a little bit of notation. I'm going to let a strand labeled by sim k. I'm going to let this denote the image of the kth symmetrizing idempotent under the functor Curvy envelope of data TL to Curvy envelope of Bar-Natan. So you should think of this as an object, not of the annular Bar-Natan category, but of the Curvy envelope of the annular Bar-Natan category. And remember, I said that the annular Bar-Natan category governs the ways in which I can cable my Khovanov, like my Khovanov invariant. This object of the Curvy envelope represents the Khovanov's colored homology, the kth colored homology. Anyway, we have natural morphisms. We have morphisms that take sim k with a concentric circle kind of around it and kind of maps that to the kth symmetric power, this is the k plus first symmetric power. In the temporal Lieb language, this would be the morphism that just takes so you take one strand and kind of yeah, that's this morphism in the dotted temporal Lieb category. And in the dotted temporal Lieb category with punctures, we have, so if, not with punctures, I'm sorry, with boundary. So if I have kind of any object in the annular Bar-Natan category without punctures, I have morphisms like this. Okay, so in this sort of two-pointed annular Bar-Natan category, I can perform an isotopy and then a saddle And this is basically where the maps involved in the handle slide come from. So if I specialize the case where around the puncture, I have a little Kirby color. Then here, if you zoom in, you see a Kirby color with a little concentric circle around it. You can map that to the Kirby color omega I plus 1 by assembling all of these dudes together. So all of these maps assemble, I didn't say this, I'm sorry. All these maps assemble to a map from omega I plus 1, from omega I with a circle to omega I plus 1. Okay, so it's actually very easy to construct a map from omega I with the strand to the left to omega I plus 1 with the strand to the right. And some not so difficult calculus in this data Taylor-Leib category tells you this is in fact an isomorphism. So that's the handle slide move. Okay, so that might have been a little opaque, but yeah. So this is the theorem. So we have this this version of the handle slide move, and I don't know. I know we started a little bit late, but maybe the thing I want to do is I suspect you guys have a number of questions. So I want to maybe stop here and give you guys a chance to just barrage me with questions, and I can try to answer them. So yeah, thank you. That's right. Yeah. Yeah. Okay. So I should probably, yeah, that's right. I should.
Can you repeat the question, please?
I'll repeat the question. Yeah. So Melissa asks, so this Kirby color is supposed to model the attachment of a two handle in the skein lasagna invariant. Basically using what Manolescu-Neithalath have already said about two-handle attachment. And I think Melissa's question was just, can I go over that bit roughly?
Can I add to that question?
Yeah.
Less fair, really unfair question. I've got a two-handle.
Yeah.
With a zero handle, a couple of two handles.
Yeah.
Can I use this to calculate invariant? Is that what this does?
Yeah, I mean, yes, but you need to know. Yes, but you need to know, like the Khovanov homologies of you take the so the question is, can you use it to calculate an invariant of a four-dimensional two-handle body? And I can't say anything new here. All I can give is what we believe is a reformulation of Manolescu-Neithalath. I just want to emphasize that this is not. I don't want to claim more than. Yeah. So.
Am I right? The two questions go together. Mine's the more general version.
I think they do go together. Yeah. So, but in order to compute the thing like whether or not this completely agrees with Manolescu-Neithalath or with skein lasagnas, I think is still open. But if you were to actually do calculations, what you would need to know is, so you would draw your whatever I don't know. You would draw your attaching spheres, you're attaching circles for your two handles. You would need to know. So you would need to know the family of cables of these things. This is really what Manolescu-Neithalath tell you. you would need to know cables of these things with appropriate framings. You would need to know not trivial cables. So replacing component L1 with this guy, that I will call that a trivial cable. But you need to understand cabling with symmetric powers. So basically there's a symmetric group action on the Khovanov invariant of a trivial cable. And you need to know the Sn invariant summand of that. And then once you have all of those are the terms in this colimit. You need to understand the maps in this directed system given by dotted annuli. Maps in this directed system are given by, so one cable and the next are related by these annulus maps, these cake pan cobordisms. You need to understand, and the cake pan cobordisms themselves are 0 when applied to the symmetrically colored thing, but the dotted cake pans are not necessarily 0. So you need to understand these morphisms between guys given by dotted annuli, and then you need to take the colimits of those. So yeah, it's really still pretty difficult to compute. And okay, now to Melissa's question, how do you actually, why is this relevant for two-handle attachment? Yeah, so the picture, okay, so skein, what is the skein lasagna module? The skein lasagna module, this is defined by Morrison, Walker, Wedrich. So given a four manifold with link in its boundary, should be a no homologous link in its boundary, the skein lasagna module of that pair is a vector space. It's a bigraded vector space. Basically spanned by, sorry, ignore this picture for a second, spanned by decorated surfaces in your four manifold, whose boundary is your prescribed link, mod relations. So you should think of this as an analog of the skein relation, or the skein module of a three manifold. So your decorations are like, so your a typical surface is like, and I'm sorry, I didn't kind of add this picture beforehand. But let's see if I can attempt something here. So if this is a picture of my four manifold, and here is my link on the boundary, whatever, my elements of this skein lasagna module are really, so I have to choose some balls in the interior of my four manifold and some links in the boundaries of those. And then I allow my surfaces to sort of terminate on these little balls here. And the decorations are Khovanov homology classes of these guys. So it's like, so to define the Bar-Natan category, we have not just cobordisms, but really decorated cobordisms. The decorations are like dots. A dot you should think of as being the non-trivial Khovanov homology class of the unknot, you know. And this is sort of something similar. You allow surfaces in the four ball, and the surfaces carry like dots, but a dot is a little bit more complicated to describe in this setting. It's a, maybe you should think of it as like a cone-like singularity with a Khovanov homology class at the singularity. It's a Khovanov homology class Yeah. Anyway, this is the sort of definition that I didn't want to go to in too much detail, but this is the skein lasagna module. And then the question is, how do you understand two-handle attachment? So the basic picture is, okay. Yeah. So I have my four manifold with a two-handle attached. This little green region is supposed to be the attaching region for my two-handle. This guy, let's say, is my original link in my four manifold, but surfaces in my skein lasagna module, of course, might run over my two-handle. So I will invite you to think of the attachment of a skein of a two-handle as like taking a quotient. Because, well, that's what it is, right? You basically just killing off some elements, and by one, you're killing off some, anyway. So what you should do is you should imagine forgetting about your two-handle, you get the sort of original skein lasagna module with union like some, oh my goodness, I'm not going to say this very well, I apologize. So the statement is the skein lasagna module of omega, or sorry, of W union a two-handle relative to the original link should be thought of as a quotient. You take the skein lasagna module of the original four manifold, but where your link is L sort of union some Taurus, not some like parallel copies of the attaching circle of that two-handle. Where K is the framing. Mod relations. And those relations are basically, okay, so those relations are the following relations. They're basically the Bar-Natan relations. So let's zoom in on the attaching region. Let's say we have a pair of parallel copies of our attaching circle. And I look at the sort of Annulus map, this cake pan map. Well, this represents so when I draw a piece of a surface, the intention is that it represents really a closed surface after attaching so many copies of the core of my two-handle. So if you were to then follow this with the like gluing on as many copies of the core of the two-handle as you need to complete this to a kind of a closed surface, you get 0. So if you take the cake pan and cap it off with, in this way, you get just a naked sphere with no dots, which is 0. If you took a dotted cake pan, sorry, that's supposed to be a dotted cake pan, and then cap it off, topologically that is a dotted sphere, so you get 1. And so the relations that you impose, and this is really what you find in Manolescu-Neithalath, is you kill certain morphisms between cables of this attaching circle. So you kill. So you set a dotted cake. You set this guy equal to 0. And this guy equal to 1. So setting this guy equal to 0 is roughly speaking like taking the image of a symmetrizing idempotent. Remember, the symmetrizing idempotent is somehow the thing that tends to kill cups of this sort. And then setting dotted cup equal to 1 is achieved by taking this colimit. I'm sorry, that's really not a very great explanation of what's going on, but I could try to say more out of the spotlight. Thanks a lot. Oh, yeah.